Hello and welcome to our webinar, The Living Heart Project, Reverse Engineering to Anatomical Modeling. My name is Michael Gans, Senior Program Manager for Life Sciences at Dassault Systèmes, and I will be moderating this session. This is the fourth webinar in our 5-part series, Model-Based Systems Engineering for Life Sciences Applications, in which we are covering numerous topics we hope will help you advance your MBSE practices. It's my pleasure to introduce today's speaker, Ryan Benishek. Ryan is an industry process consultant at Dassault Systèmes. He received his bachelor's and master's in aerospace at Wichita State University. He has worked for the National Institute of Aviation Research, or NIAR, at Wichita State University, where his primary focus was reverse engineering and additive manufacturing. The latest projects at NIAR include being the design lead for an SUAS platform, as well as a project lead for aircraft accident reconstruction. At Dassault Systèmes, he specializes in reverse engineering, additive manufacturing, design and simulation, and systems architecture. And now, without further ado, I'd like to turn the webinar over to Ryan to begin his presentation. Ryan, it's all yours.
Thank you, Michael. That was a great intro. Yeah, like Michael said, I've been working at Dassault Systèmes for about 3 years. About the past 2 years, I've been working on the Living Heart project, working to take the design and reverse engineering aspects of that model and make them a lot more robust and a lot more systematized for use within the project. So with that, part of the beginning of this presentation is, what's our motivation for reverse engineering our Living Heart human model? For those that aren't familiar, I'll give a quick overview of the Living Heart project itself. But beyond that, why are we going to these links to actually reverse engineer it and not just use, a static model for the heart model? Why go to the links to actually reverse engineer it and make it connected? So the original, for those that aren't familiar with the Living Heart project, right? It really has spun off over the past 6 years, back in 2014, of can we actually virtualize and simulate a living heart model with help from the FDA and the CDRH Foundation to actually see if we can do that. But about last year, we started to have a slightly broader focus with this living heart model. Once we proved that the techniques and the efforts were possible to actually virtualize a human heart, we realized that we wanted to take this even a further step further and go start using computational modeling to start creating a clinical trial for medical devices. So can we go from years to days on a clinical trial? Obviously, that's a pretty ambitious goal, but our main focus here was that in silico bench test and animal tests and cadaver tests and animal trials and candidates and all of those pieces, can we systematize those and virtualize those to make those quicker for turnaround and do less animal tests, get rid of the cadaver entirely, and in the animal trial, and actually have a virtual human that we can use, a virtual human surrogate that we can use, right? So instead of doing a whole bunch of animal tests, we just do an animal validation test, right? And we basically take all those bench tests and animal tests and cadaver tests and combine those virtually. Still make sure that we have that validation effort, right, to make sure that everything in the end is exactly what we're looking for, but greatly reduce that cycle down and do a lot more iterations in silico, right, using both a bench model and a human model in the certification process, right? And our main goals there are to save time, save resources, right? Have better designs because we can have a lot more iterations ran, right? We don't have to spend the time for all that development. And this is really one of the first efforts from the FDA to go down this process of doing a lot more in silico trials, to really do these clinical trials virtually on something like medical devices, for something as critical as heart medical devices. So when we go into the application of this, what we're looking at are numerous different medical devices, numerous different aspects of this device We've got rings and occluders as part of this to see their stresses, to see how well they expand, see how well they deploy within the model, see how well the impact of placement of pacemakers and leads affects the performance of the heart and how well it can beat. Catheters, stents, and grafts, as well as doing valves and repair. So looking at repair wings, making sure we don't have any regurgitation. Lots of different aspects of this model are starting to be used for virtual simulations, right? So it's not just we're not just looking at a pacemaker lead validation. We've got a framework open enough that it can handle a lot of these different aspects of medical devices, right, for validation. So I just wanted to give that as a reference of kind of the history of where this heart model has come from. Getting into the specifics of the heart model itself, we've got numerous different pieces about all of the major aspects of the heart are kind of split up in one for ease of simulation, so you don't have such a complex model to try to manipulate. We do have both of the chambers connected just because they're so integrally combined. So we have the left and right ventricles connected down there, but we have like the aortic arch, the pulmonary arteries, all of the valves, as well as the chordae and some of the ancillary arteries and veins split out as well. So this is kind of just the overview of the pieces of the heart itself, and all of these pieces are connected together. All of them are physically talking to each other, so they all interact with each other. If you modify one surface at the at the boundary, it updates both of them, so they stay tangent continuous and connected. So all of these pieces are quote unquote connected together and are all part of the same assembly for doing full heart models simulation. Okay, so as part of this, one of the big questions you might be having is, where does this reverse engineering aspect fit within the systems engineering domain that you guys have been covering for the past few days, or few webinars, excuse me. So part of this aspect is to create a system context for you to do your simulations in, right? And so if you take a look at the systems model as an integration framework, we've got several instances of the system modeling, specifically the SysML breakdown of your models into 1D elements. But how does that actually fit with something as complex as the living heart model, right? So I just wanted to give an overview of how this system model is decomposed, right? We've got some external requirements coming in, then we have a system model inside SysML, and basically what we're going to do is extend that with a physical model to do some integrations. So what does that look like in terms of Dassault specifically? When we're starting to interact with the 3D experience platform, what we're trying to do is to, if you're doing a proper systems model, right, and a proper digital integration, where does this particular living heart model fit? It fits inside of geometric design, the process composer, and the native simulation. What that means is we can take our external requirements, tie them into our requirements and parameters widgets, link those directly to geometric design, right? So we can have a specific parameter like an annulus diameter must be this, or your device must fit within a certain standard deviation of a heart, right? So all of those pieces can be tied directly to the geometric design. But beyond that, you could say like it must be able to handle a certain pressure. It must be able to handle a certain level of elastance of the heart material itself. That's where they can tie directly into the process composer aspects from those requirements and parameters. And beyond that, we can even tie your Cameo, No Magic SysML models directly in through that same link to start tying in through the process composer link through 3DX Connect. So you can start looking at safety observers, or start looking at on some more complex devices that have some signaling or have some timing interactions with the heart to actually make sure that everything's in sync and working together through that process composer and 3DX Connect link to directly tie those to the simulation. So you can see if you start simulating your Cameo models, parametrics after you get through the behavior and structure decomposition, right? you can start simulating those parametrics and start having them interact directly with Process Composer. And so all these aspects can fit into either the electrical twin of the heart, it can fit into the simplified fluidics twin of the heart, or even the mechanical twin of the heart, right? All those are coming from that same initial living heart model. All those have those parametrics that can be read through the Process Composer, through the native living heart simulation aspects. The ones that we're going to be focusing on primarily today, and this is where I've been really focusing a lot of my efforts, is on the geometric design and connecting that into Process Composer and all of these other aspects to build a testing method and model that's robust enough to allow a lot of your other devices that are modeled, more traditionally with the model-based approach, is to interact with it. So, not to say that we're not going to cover those, but just to let you know, we're still, building this model and getting it ready for final validation for delivery, at least on the geometric design and Process Composer side. And once we get that, then we can start saying, how do you want to parameterize your model? What are your key parameters that you're after? What does a representative device look like when it's interacting with this? If it has a Cameo model, SysML model representation interacting with these, this complex level of the model. So that's kind of the focus that we'll be focusing on. I'll start with the geometric design and specifically how we started creating this, and then we'll start branching that off onto how we can start looking at behavior aspects from the native simulation, as well as starting looking at approximations, machine learning aspects of this model in order to make the simulation efforts a lot easier. Okay, so let's take a look at reverse engineering anatomical geometry. So the purpose of this is to create a robust and easily updatable model that doesn't break. And so there's a lot of different ways to build a geometric model from digitization data, whether it's coming from CT scan, MRI scan, to even just 2D images, right? The process that we're going to be using is what we're calling a subdivision surface. This is more keen to freeform sculpting and a lot of light industry 3D graphics tools, and less so on the CAD aspects and the design and simulation aspects. What makes this nice is you have the ability to just directly pull on these nodes of this surface. So if you take a look at the square, for instance, those are the 4 nodes representing the sphere, virtual nodes that are floating out there, and you can take those 4 nodes and deform the sphere into a lot of different, any complex shape, basically, just by moving those 4 nodes around, right? So you start off with the square, end up with a sphere after it's been refined enough. And what this allows us to do is have a simplified surface representation that is very curvature continuous. It allows us to have a much higher quality mesh, and it makes it so that it's a pretty straightforward to say, I want to move this portion of the surface, and you just pull on it. A lot of these other aspects are power fitted surfaces or surface networks that are a lot more complicated to try to fit and don't offer you the freedom to manipulate the surface after the fact, right? It's kind of a one and done thing, right? So it can take a long time to create a high quality surface, if at all possible, without using subdivision surfaces, and modifications of that surface are nearly impossible. And that's what we had found whenever we had started this back in 2014 and 2015. We had just a static model that was surfaced, very well surfaced, but it wasn't able to be updatable, or if we had small areas of surface discontinuities or some other aspects, we had to manually manipulate the FIM mesh underlying that, right, which makes it very difficult. And a lot of these simulations that we're doing are with explicit meshes, so that getting a very good mesh quality is quite tricky whenever you're just dealing with a static, tangentially discontinuous input surface. And so it took a lot of effort to get that mesh quality at a high enough quality that simulations would actually one, converge, and two, simulate quickly. So what I'm going to start off with is showing how we can start creating this anatomic geometry from a mesh or an STL using the subdivision techniques Again, back when we started this, we didn't have a lot of these techniques available to us, but this organic shape modeling started becoming really popular with topology optimization, started becoming really popular with doing some very complex topology optimization shapes. And so their surfacing tools were greatly expanded about 3 or 4 years ago to start being able to draw directly on, start doing reverse engineering on more organic shapes. And that's really where the tool bench started getting a lot of additional functionalities that made it very powerful to create these subdivision surfaces on any type of mesh or STL. And the whole purpose with this was to spend the extra time, create a high quality subdivision model, because we could have just automatically surfaced the model and got a subdivision surface, but the mesh quality, the quality of those patches and where those nodes are located aren't as intuitive or aren't as simplified as if you were to draw it manually, where you can explicitly define it. So with that, I'll play the video and we can take a look exactly at what I'm talking about here. So in this case, we're going to take a look at this with a ulna. And what I'll be doing here is drawing some patches directly on the STL of this ulna. And what I'm doing here first is creating these processes of the bone itself. And what I'm doing there is so that I have a region of the ulna, in this case the process of the ulna itself, that bump of the ulna that's very well defined. In this case, creating it as a ring, so it's very easy to manipulate and adjust that process, right? So that we can say, once we close this face, and we'll keep going through it, and you'll see it starting to be closed. Once we close that face, we'll have the ability to very quickly parameterize that, fit it to the surface that you just saw there, and with just a few patches, start recreating that process. And the purpose of that is to have a very good underlying topology for easy manipulations, for easy parameterizations, so that if somebody wanted to change the angle of the process of that bone, or the height of the process of the bone, or cross-sectional widths, we have very easy patches to tie to the complex parameter or whatever we're trying to match, and get a good fit. And so while you can automate this, right, so you don't have to manually draw these patches, as this person is doing, step by step around this bone process, you just don't quite have that level of fidelity that's needed to allow this to have rapid iterations. Just because generally when you're auto surface, it doesn't quite know, what areas of the surface do you need less data in, or what areas do you need, more patches in to fit better, right? And so when you manually define it, you can, explicitly control, oh, I only need 10 or 12 patches to represent the shape of this, process, right? I don't need any more than that, and any more than that's just kind of wasting your time trying to manipulate all those nodes around. So you can see relatively quickly, so those were both in real time. Relatively quickly, we can start extrapolating and start fitting this mesh to get better results as we're manipulating it. And so we can use these extrapolation techniques, these hole fill techniques, to start building this model. So you'll see it here is we'll just quickly hole fill this model. And then you can see just a few clicks and we can basically completely close this entire model. And what that allows us to do is take this surface, and even though it's not fitted directly to that process, we can then very quickly manipulate these 3 nodes and build out a very complex surface. And so here he's just manually getting it close, and then he'll fit the rest. And this is basically what we did on the entirety of the heart model, from both scan data and from the original surfacing and fin mesh that was created. In this case, we actually needed a little bit more surfacing there, so we added an extra node, so now we now have that ability to node, right? So we very quickly added a little bit more complexity to the surface, and that allows us to get a much better fit on this process, right? So it's always a trade-off between complexity of the surface and complexity of your part. But here we just very quickly created those two processes, and now we'll create basically the final ring connecting these two surfaces together. So again, we're just drawing directly on the STL to build this surface. So the reason we go again through all this work is so that we have a nice topology that we can use for one, parameterizing, and two, having enough data to fit properly. So there we just blended the two surfaces together in one click, and we'll do the same over here on this side where we'll blend the two surfaces together. So now we have basically a continuous ring of surfacing. We'll do the same thing here, and now we have that continuous ring. So you can see these merging tools are very quick to get a very nice and complex surface. And once we have this ring done, again, we'll do the exact same thing we did with that process of the bone, just fit across the top there to get that surface built, and then we'll close off the ends, and we basically have those 4 nodes representing that top of the ulna. Again, this is with bone and with a bone, but this is the exact same techniques we would use whether you're creating papillary structures or a complex atrial surface. And from there, once all we have to do is just extrapolate it down, simplify some of those patches, and then just do a fitting, and we have a very high quality ulna surface that we can then say that this is a template surface and is now ready to be used for further manipulations. And that surface is now at a high enough level of quality that we can mesh it very nicely. So that was creating anatomic geometry using a mesh or STL. And basically, we have a couple of workflows that we extrapolate from that, right? So we have the initial import of your digitization data. We have the alignment of that data. We have the morphing of the STL, whether we're using the Imagine and Shape tools or even some generative shape design tools to actually morph that data and get it into position. And then all we have to do is update our structural model inside of our mechanical scenario and simulate it and get our results back. The purpose of this, right, is to create those is to have that template model basically already in place. I'll do all the hard work for you so that if you get a new patient geometry in, you're no longer having to reset up a simulation or reset up surfacing or reconnect any of those links. They just stay connected because we're just using that same template surface and just morphing it to the scan data without ever having to recreate any of the links to the structural model or mechanical scenario creation. So that's really the key, right? Is before we went down this reverse engineering route, we were really starting at the structural model and mechanical scenario creation phases, and everything else wasn't connected, so it didn't really matter. So you basically had to recreate a template model every single time and then reconnect it into the structural model, right? And so it was very time consuming to go down that process. So again, just a kind of another workflow to view this, we would import our patient data, align it, correct it, do anything we else need to it, get it into position, and then start morphing locally our surface to fit that shape, fit it exactly, make sure it's validated, and then we have our geometrical surface ready to be fitted. And we'll talk about later in this webinar how we fit behavior to that. So again, just as a quick video just to show, we'll take a look at our ventricle model. It's very easy to manipulate the subdivision surface once we get this template model built. And the purpose of this is to show, kind of the whole reason we're doing this, right? So in this case, we are manipulating the diameter of that, of the structure there. We're, increasing the wall thicknesses in some areas. We're, creating a bulbous region of this model itself. And the reason we're doing this, right, is just to show how everything stays connected whenever we start doing our manipulations. And so as we're manipulating this model, all of these surfaces are connected. So I'm just going to pause it right here. All of these surfaces are connected and stay together. And so once we update that model, our local wall thickness stays the same. And if we want to change our local wall thickness of any of these regions, we can pull on that green surface instead of the pink surface. And this is really the purpose here, right? So all we have to do is just update, and the mesh is a high enough quality of a mesh that we don't have to, worry about any of the thin meshes failing. just because the local mesher reruns that again, and any of those local meshes stay in high quality, right? So now that we have our template model linked, we can now just take a look and import our geometry, in this case a pericardium surface, and all we're doing here is just getting it locally close to, so our topologies are relatively in the same ballpark. And this can be automated. We're just showing here how you can do gross manipulations, either manually and get it fairly close, or take it and automatically fit some local areas on this model. But what we're just doing here is taking our template model and morphing it to any type of geometry. So in this case, we were morphing it quite a bit, but this is a pretty good example of just how variable all these human anatomies tend to be, right? So once we get it morphed close, then we can start doing more accurate fittings that you'll see here. And once we get it close, then it's just a simple fit, and then the mesh is ready to go. So we get it fit relatively close, and then we can just select all of these nodes and say, we're fitting directly onto that mesh. So that's kind of the process that we would go if you were doing patient-specific data, right? Is build your template model out, whatever the case may be, right? That has all of your stresses and material properties applied to it, and then you can just morph your surface and the techniques that we've kind of implemented on the living heart model. Do that same approach on whatever template model you guys have, if it's beyond the heart model itself, and still have all of your simulations ready to go and all of your templates ready. So that's where the rapid iteration of models comes in, is how do we start taking that once we created the template model, right? So in the case of the heart model, it was several months to build the heart model, but once we have it, it now can generate many iterations of models very, very quickly without having to worry about reconnecting any surfaces, or rebuilding groups, or rebuilding any other data. And so that allows us to do very rapid iterations of our models. So once we got our baseline model built, we can now start take a look at cardiomyopathies, take a look at pediatric scale models, right? To scale down the whole model, change the material properties, and we're good to go, right? And then we can also start looking at disease states. So in this case, we've taken a look at just beyond cardiomyopathies. We included VSDs, ASDs, tetralogy of Fallot. Data's on that pediatric scale model once we got those validated. All right, so just to give you kind of a overview of the process that we would go through, specifically for the pediatric scale modeling, is we have a lot of population statistical z-score information. And so our goal isn't to hit everything obviously directly down the median, but just make sure that whenever we scale our models, or do any of our things, that we're falling within our z-score values of our entire model. So we can take this entire model, scale it down, take a look at any measurements, right? Since it's just 3D geometry, have those measurements reported out directly as parameters, so we can see those in real time as we're manipulating our model. So in this case, you could also take a look at the FEM of the model itself. You could take a look at and see how that's being modified, and then once you get it into place, you can start freely manipulating this. So, example, for this ventricle septal defect, we can very quickly take this original subdivision surface and start morphing it, manipulating it, and really start changing exactly what that ventricle septal defect is, and still have it tied directly to a simulation object. And again, our whole purpose is to have our z-scores to get a standard model for, in this case, for validation and visualization, and for simulation, right? Or you could again have this directly, instead of being a generic population model, have this specifically for patient-specific data. But in this case, we were creating a general population model that represents z-scores and averages, and making sure that all of our results that come from the simulation are falling within the range. So this pediatric example, right? Again, We got the pediatric statistical information, scale down our heart to their correct appropriate size. All these services update. And so this was a pretty good scale because again, it's a pretty large reduction in size, about a length scale of 2. So that's, like an 8 times smaller volume in terms of, area. We're down to a 4-month-old pediatric heart, so it's pretty small. But it was a very good test for us to make sure that, nothing drastically broke whenever we scale something that small, and all of our, services could update it accordingly. In this case, a pediatric heart actually has a shortened ventricle long axis length, right? So that you can see over there on step 3, how we can quickly just take that entire model and just translate it up to get a shorter ventricle axis length, while keeping the top vasculature and outlets in the same relative location. So then we can check and update those temps to make sure everything else looks good, right? So there's that pediatric heart after we scaled it, and we're got that one validated relatively quickly. So what does this mean, right? Building a new heart model does take a few months, especially on a heart model, something that complicated, right? Making sure all of our values map. It's basically as complex as you can get in terms of a simulation, right? You've got an electrical one that we now have to tie to geometry. We've got a fluidics model that needs to be attached to it. We've got obviously the mechanical model itself that all needs to be attached, right? So it was time consuming, but very worth it, because on a minor adjustment like wall thickness scalings, papillary additions, things like that, it's a couple of hours to get a new simulation model. For major adjustments like fitting to an STL and getting it exactly in, that's about 1 to 2 days worth of turnaround time. And so it's very quick to do these minor adjustments and have your model fully connected and simulation ready. The approach that we were using in the past, it was several days to just get an orphan mesh with a cleaned up FIM mesh that was ready to go. And to have all those FIM definitions redefined and reconnected, that was many weeks of effort to get those reconnected and reattached if we were using those third-party tools. So that was what we started using internally, and saw very quick turnaround time, a lot of iterations that we could do very quickly on our heart model. So what was taking us, sure, we had a fairly large lead time going up into this, but once we got the model up and running, it was really off to the races. And what I mean off to the races is at this point here, we had finalized our heart model. So this was a 6-month effort leading up to this point. And from there, every one of these dots represents basically a final validated model that was up to simulation level and ready for simulation and checking. So we have that was simulation ready to about 15 to 20 models that were all simulation ready, as well as starting to be able to branch off from those and just have very quick iteration turnaround time. So we took this to looking at pediatric scale models over here, to disease state models over here, right, to just a few other particular models that we were looking at. So very, very quickly started getting multiple different iterations being built. So we've taken this further and started looking at how we can start building model libraries, in particular this left heart model with the mitral valve, and this is just the left heart submodel, and this is what we're primarily using for our clinical trial, right? So that almost bench test level of simulation. So we don't need a full heart model with all 4 atria, or with all 4 chambers, the 2 atria up above and the right ventricle there, right? We've only really are caring about maybe a device that's interacting with the mitral valve, and so we only need to take a look at the submodel at this level, right? So we can once we got the submodel built, again, it was about a few months of effort. Now we can very quickly get a lot of iterations now that everything is tied together and connected through this reverse engineering approach. Similarly, we've now started looking at the pediatric scale model and are looking at pre and post treatment effects of this model. So in this case, we're looking at a ventricle septal defect here with a patch being applied to it, and how that changes your wall behavior, how it changes your pressure across the model, and also for both the patients to look at, see exactly what's happening and occurring on their heart, and for students to take a look at and understand exactly what that treatment procedure will look like moving forward. Okay, so now that leaves us from the rapid, creation of those models. Now let's take a look at how we can improve the simulation times, specifically of these models. Again, all leading back to that systems engineering approach, where we can start tying that in with a, SysML model, start tying that into your requirements and parameters, because it is not a simple thing to simulate a four-chamber model and get a design of experiments from it, right? That's an 8-hour simulation for one beat, right? And so it's quite consuming to try to do a trade space analysis using those approaches. But before we get to that, what are we looking at specifically for trying to drive these simulations? So this is the start of the connection of going from requirements and parameters to driving complex surface geometry. And one of the things that we can do geometrically, right, is tie these to parametric surfacing techniques. So tie this complex organic surface to more simplified representations of geometry. You could, of course, always tie the nodes of the surface, XYZ positions. That's just a lot of parameters. And so the goal with this is to simplify the amount of parameters that you need to control, right? So maybe you only care about an average radial value of your mitral valve annulus, right? So really, that's just a one radial parameter. Sure, you have more complex local shape to that, right? It's more of a D shape or whatever, but maybe you just kind of care about the overall scaling size, radial scaling size of that model. You don't care about locally modifying the shape. You're just more concerned with overall annulus size, right? Is you can tie that to one single parameter of geometry, link all those nodes directly to that wireframe geometry that represents that one parameter, and then you can start running this through an optimization process composer, start looking at boundary value problems, right, to get an exact, area output on your annulus. And I have a video showing this specifically that we can talk about how we would do this parameterization process on geometry. Again, if you have other parameters of requirements parameters, or boundary values, or specific population parameters that you're looking to simulate against as part of your validation process, you can still tie those, as part through the simulation, right? All of those are parameters that are accessible as well through that process composer loop, or directly just in the simulation, like material property parameters, or a lot of parameters inside of that model that you can really adjust. And so what we did was give you a quote unquote like blank slate of your model, and then depending on how your companies are looking to parameterize this geometrically or through the simulation, right? All those parameters, are kind of the IP that you guys would be controlling on your model going forward. Let's take a look at this parameterization process, specifically geometric parameterizations. So we've got a couple of them that we can take a look at. One is mitral valve area, one is ventricle length, one is trunk angle, and then combining all of those together into an optimization to look at specific volume or area values, right? So we can actually target this. So in this case, I've just kind of stripped everything away, so we're just taking a look at the epicardial surface of this ventricle. In this case, we're just going to take a look at the mitral valve area of this ventricle. So we have our wireframe geometry starting to be created. That's going to be tied to the model, right? So we have a direction, an outlet direction of our mitral valve that we're looking to scale, a radial value in, right? So I have my radius value that I can easily adjust parametrically, and basically what this will allow us to do is, kind of centrally scale just those nodes that we want to tie to this wireframe surface to that radius value. So there you can see all those nodes just at the top annulus opening are going to be tied to this radial value. So now what I'm going to do, right, is create a length parameter, call that, mitral valve radius, and then we'll have a measurement value being measured directly from the geometry that is, our mitral valve area, right? So we can set these up so that we have, a boundary value problem going from one way to the other, right? We want a specific mitral valve area, so we type that in, and then we need to find the quote unquote mitral valve approximate radius that represents that on adjusting it, or maybe we adjust our radius and see what area we can hit, right? So we got two different kind of approaches that we can hit on this. Again, since it's a more complex surface geometry, that while we can adjust the radial value and get a measurement out, right? So here I'm shrinking it. You can see it very quickly updates. That's one parameterization we can do. There's basically an infinite number of parameterizations or parameterization styles you can choose from, right? Basically, the max number would be the XYZ location of every single node of the surface if you really want to get down into it, right? So there's a whole bunch of parameterizations you can do on this model to represent it, any sort of style. In this case, we're creating a volume surface, just a very quick closed volume to measure this epicardial volume area. Obviously, if we were doing this in real life, it wouldn't be the epicardial volume, right? We'd be measuring, right ventricle volume and left ventricle volume, but just as an example here. And again, these are just what I have chosen, right? The ways that you can drive these nodes are pretty much limitless. So I'm just, here just showing how we have some vector direction that we want to pick to scale this part in. In this case, we're trying to hit the axial direction to go. So basically, what we're doing here is just tying all these nodes and all of these parts together as a vector that represents the length of this ventricle. So we'll skip it ahead just a little bit here, so that we're now taking a look at the ventricle length itself. Right, so now that we've tied everything together through wireframe, I can now just type in my ventricle length and start getting adjustments, right? And so these are the types of things that we're trying to enable through this workflow. Is how do you parameterize your model enough to capture all the relevant details for your validation studies, right? So that's how we do that parameterization itself. The only thing I was going to cover here is once we have all these parameters in place, right, we can now set up, in this case, an optimization to specifically target specific values, right? And again, this is me manually doing it, right? There's nothing stopping you from wrapping this inside of a process composer loop and having this being automated, so you don't have to manually calculate it, run it, and set the values. Just as a more visual example, so you can see this running, we're using the CATIA optimizer here. So then we have our radius of 23.312 gives us exactly 1275 on our area. Right, so we can start to see that convergence. So what does this lead us to, right? Because we talked about our parameterizing, in this case geometry, but how do we take that and go a step further? That's really where our next phase of this comes from, is statistical shape analysis. How can we start looking at parameterizing this model, simplifying the amount of fundamental shapes available to us, right? So in this case, one of the limitations with traditional statistical shape analysis, if you're just doing it with nodal coordinates or FIM coordinates, right, is one, your FIM mesh can get easily distorted and give you poor simulation results, and two, that's a lot of parameters to look through. Yeah, you can get very accurate shapes, but that's a lot of parameters on your model library. So the alternative to this, or the improvement of statistical shape analysis, is tie that directly with parameters that are driving your subdivision surface explicitly, right? So instead of just getting random shapes, you can get specific principal components that actually have are tied to realistic values, right? So you can actually tie a whole population set directly to that mitral valve annulus radius value, or mitral valve area value, directly from the statistical shape analysis. So you're basically reducing the number of variables, but making them a little bit more easily readable or easily understandable whenever you start combining, these fundamental shape components, right? So your fundamental shapes are still, how you can, get certain standard deviations and certain libraries being infinitely created, so you have your population model. But now you can start tying those to a little bit more realistic values, or maybe explicit values are starting to be controlled. So the approach that we're starting, right, is this behavior modeling, right? So is once you have that statistical shape library being built, right, or you have that specific medical data from a specific patient-specific geometry, you start to use this anatomical matching approach and build an FE model that's fully parametrically associative. And in this case, for example, on that left heart submodel, looking at the finite element model and evaluating leaflet closure, right? So we're primarily looking at both the population data set or a patient-specific data set and start looking at exactly how those leaflets are closing, right? What we can then do is, so now that everything's parameterized, is we can link that into a optimization or design of experiments and see exactly how that behavior is changing over a set of our parameters, whether the parameters are a random sweep or if they're coming directly from our statistical population parameters. The goal, again, the whole purpose of that is to create a device that can better fit to match that behavior, right? Not just the geometrical statistical shapes, but also the behavioral statistical shapes, if you will, to get better designs for specific specific patients or for an entire population set. With this, we've got disease modeling that we're also looking at to directly as part of this, right? So we can start tying in our 1D fluidics model, right, from Dymola, tying that directly to our three-dimensional behavior model. So now we can start looking at, and again, this is the same thing for the electrics model and other aspects as well, right? Is now that we have these parameterized and described in 1D blocks and in the 3D and how they interact together, now we can start looking at hypertension. We can start looking at stenosis. We can start looking at more complex step defects that you saw earlier on the geometry side, but it also affects obviously the fluidics model, right? And so you have different different interactions and different 1D models that are still tied to that you need to capture whenever we're going forward in this disease modeling. And so that leads us finally to the next steps. Kind of I wanted to give everyone on this call kind of the next steps that we're looking to hit once we have this heart model fully finalized and ready to go, is to start taking this very complex model and simplifying it using some multi-fidelity analysis, some machine learning capabilities, so that we have quick turnaround times whenever we're doing our simulation, so we don't have to spend the efforts going through this entire ordeal to build a very complex model. They'll still use that as our validation model, but not have it be the main driver in order, so we can get our design of experiments and our population models ran very quickly. So part of the issue, right, is even parametrically, just on the parameters of the simulation, we're at 270 parameters. Just all these parameters, have a fairly non-trivial effect in certain aspects of the model. And so how can we tune those 270 parameters to just get the ones that we're really after, right, and really understand how we can have build an efficient model, right? And these are just the mechanical parameters. We haven't even talked about the geometric parameters that that also control that, and that can be thousands of geometric parameters, right, that if you really wanted to control it. And a lot of those would have small effects, but there's several parameters that have huge effects, right? Like ventricle lengths, wall thicknesses, and all sorts of aspects of the geometry that can also impact this. So it can really make simulating diseases quite the challenge. But our goal is to start looking at this multi-fidelity analysis with all our different models, right? Our hemodynamic model, our circulatory model, our elasticity models, our material parameters, and say, all right, what are the key aspects we're looking to get out of this analysis? And part of this portion is to build a machine learning model that can be trained from the living heart model, so that we get a very good correlation from what the machine learning model is predicting in this overall multi-fidelity analysis, so we don't have to run the full-blown sim every single time. and then do an optimization loop or a design of experiments loop from that. So that's where we've started, is in this case, we're looking at that machine learning model, in this case, a fairly linear correlation model. But just to show, we're starting looking at ejection fraction prediction from the machine learned model, and we've ran, about 100 cases of the living heart model, and start to show how the machine learning model can start having a very strong correlations in some aspects. There's some aspects like ventricle volume, right ventricle volume, that are a little less well fitted on this model, right? But this is just a start in terms of the number of parameters that we're trying to predict from this, machine learning aspect. But on ejection fraction so far, on ventricle pressures, it's doing a very good job. Those are, very, very well received responses. So it's not a catch-all end-all for everything, but it does start predicting some of these models very well and very accurately, without having that huge resource cost of actually running the full heart model, 4-chamber heart model. And so that's kind of that's really the next step that we're trying to achieve, right? Again, the whole purpose, right, is so that whenever you are simulating your device inside of this model, or designing a device to fit within the system context, right, that it's not such a long turnaround time. And so that's really where we've been focusing a lot of our future efforts, is to figure out how we can start enabling this behaviors to go into effect. Start looking at the simulation efficacy going forward, and start correlating this directly, right? So we're still in the early stages of this, but we've already starting to see pretty good results from this very quick turnaround time of getting you within the level of certainty that you need to, without having to spend the extra effort to go fully to the heart model. So that's really the future steps of where we're trying to go, right? Is to start training these models to have better responses. And with that, I have about 5 minutes left for questions. I'll hand it back over to Michael, and we can go from there.
Outstanding. Thank you so much, Ryan. That was a really interesting presentation. We'll now move into the Q&A session for today. So the first question, we understand bones are fairly rigid, and the question has started, how does the modeling account for deformable shapes like the heart muscle? And then you went into the heart example, and so he elaborated on that a little bit and said, from a simulation standpoint, how do the nodes that are assigned to the tissue or deformable structure automatically adjust or move with the deformable shape?
For deformable shapes specifically, we're usually looking at one time point, right, diastole, usually for the heart, and we're hitting that. For how they move, if you're looking at, we usually try to hit the same, for a deformable structure like the heart, we're trying to hit the same part of the cycle, right? So if we're modeling we're usually modeling for diastole. We're trying to get the simulate the CT scans or whatever you're after captured at diastole for your model. So that's what I would say. As for morphing them, whenever they're not moving with the simulation, right? Once we generate our diastole shape, right, for instance, the fin mesh then takes over, and that's how it's being morphed. So hopefully that answers the question going forward.
Interesting. Yeah, I think so. The next question, what is the current status of the new living heart model for use?
Oh, great question. Yeah, so the current status of the heart model is that we are in our final bits of validation. Hopefully we can have a pre-release to the Living Heart project member community, so we can get their feedback and input at the start of the next year, so very early next year. And then we're looking for a mid-release on this new heart model that has these fully connected shapes, mid-year next year. We're still working on exact methodologies to make sure that everything is packaged so you have enough tools to allow you to morph the heart correctly. But we're looking for about a mid-year release next year generally.
Perfect. And I think we have time for one more. What other advantages do subdivision surfaces have for anatomical modeling?
Yeah, great question. All right, so for anatomical modeling specifically, let me go to a extra slide. We have several advantages from these, right? The biggest one actually, besides the ability to just pull on a surface locally, is this tangent continuity, specifically for generating a high quality fin mesh. We've seen quite a bit of improvement once we get to meshing off of subdivision surfacing that we haven't really seen before from a lot of the other reverse engineering techniques, like network of curves and things like that, where these subdivision surfaces, just by their design of how they're formulated, pretty much always guarantee at least tangent continuity and usually curvature continuity. And those produce very high quality fin meshes just automatically whenever you do a modification. So those were kind of the key ones that we've used, right?
Okay, great. It looks like, unfortunately, that's all the time we have questions for. Ryan, thanks again for your time and expertise. It's obvious that the audience found this information very useful and interesting. Thanks everybody for joining, and we will see you at the next one.
Thank you, Michael.